You guys are doing okay? Any questions from last time? Anything that I said last time that didn't make sense? Okay, so today I want to finish up section 10.2. The topic is arc length. That is, suppose we are given a parameterized curve C, and the parameterized curve C is given by x equals to x of t, y equals to y sub t. T is between a and b. So here I have a curve where the parameter t varies over a finite interval, so that I have my curve extends from t equals to a to t equals to b. Let's say I am going to denote by r of t the point x of t, y sub t. Okay. Now, if you think of this curve as the path of a moving object or a moving bug, then what is r of a? I can think of r of a to be the initial position of the moving object. Okay, r of a would be x of a, comma, y of a, right? And what is r of b? R of b would be the final position of the bug, and r of b would be x of b, comma, y sub b. So at t equals to a, you are at r of a. At t equals to b, the bug is at r of b. Now, for any given t, r of t would be some point on the curve. Okay? What I want to know is what's the length of the curve. So why do I care about the length of the curve? Well, obviously there are many applications of that. One application would be that if you are thinking of this as the path of a moving object, then the length of the curve will give you the distance covered by the moving bug over the time interval from A to B. Okay? So first of all, in order to come up with the length, I am first going to concentrate on the problem of finding the distance covered by the moving bug over that time interval. So first of all, I am thinking of the curve as the path of the bug, okay? And I want to find the total distance covered by that bug. So let's see how we should be coming up with that. First of all, if I have a bug moving along this curve, r of t specifies the position of the moving object, right? So r of t is the point on the curve. It's the position of the bug at time t. Now, I am going to think of r of t as a vector. So I'm going to think of r of t as the vector where the tail of the vector is at the origin and the tip of the vector is the position of the bug. The tip of the vector is the position of the bug on the curve, and the tail of the vector is at 0. So the yellow vector that I have, that's r of t. Okay, that's the position vector of the bug. Now, what would be so if I have the position vector, then what's the velocity vector? What should be the velocity vector? Well, the velocity vector should be tangent to the path, right? Because if you're moving along the path, at the point r of t, the velocity should be tangent to the path, right? Because the velocity should tell you the direction of movement. The velocity should tell you the direction at which at which the bug is moving, right? So the velocity should be the tangent vector at that point, but then how do you find that tangent? How do you find the velocity vector then? We know it should be tangent to the curve at that point. How do you find the velocity vector? Well, the idea is that, well, let's think about this. Let's take a small number h. Let's take a small number h and think about the motion of the bug in a very tiny time interval. So we are fixing time from t, between t and t plus h. So think about h being a small, tiny quantity, okay? So we are looking at the time interval from t to t plus h. Now, what's the position of the bug at t plus h? So at t plus h, the position of the bug is the green point, or the position vector of the bug would be the green vector. Okay? At time t, the position vector would be yellow vector, right? So what's the difference? What is the difference between out of t plus h and out of t? So what is the difference between r of t plus h and r of t? What is out of t plus h minus out of t? Out of t plus h minus out of t is actually the vector given by the pink vector. So the pink vector starts at the yellow vector, at the tip of the yellow vector, and ends at the tip of the green vector. So when you subtract out of t from out of t plus h, that's the vector you get. Okay? Now imagine, somebody tell me this. What is this difference then? This difference is the change in position then, right? If I look at out of t plus h minus out of t plus h, position at time t plus h. Out of t, position at time t. So the difference is the change in position over that time interval, right? That's the change in position, the net change of position over that time interval from t to t plus h, right? Now if I divide it by h, right, what am I getting? What is h? H is the length of that time interval, right? From t to t plus h, what's the period? What's the length of that time interval? H. So when you divide the change of position by the length of the period, what do you get? You get average rate of change, right? The numerator is the change of position divided by the length of period. So that's the average rate of change of position over the interval from t to t plus h. So this quantity that I have here, this is the average rate of change of position. Let me just say position. This is the average rate of change of position. Okay? So now if I take the limit as h goes to 0, I get the instantaneous rate of change of position at time t. Is that making sense? And you can imagine that as h goes to 0, the green point is getting closer and closer to the yellow point, right? As h goes to 0. And then the pink vector is getting closer and closer to the tangent vector. Okay? So the point is, if I take the limit of the ratio, if I take the limit of the average rate of position as h goes to 0, I'm going to get the instantaneous rate of change of position. So, what's the velocity? The velocity is the derivative of the position vector. R prime of t, that's the rate of change of position, right? R prime of t, that's the rate of change of position. That's exactly what we mean by velocity. So what should be the velocity? Well, the velocity should be, you look at r of t plus h minus r of t divided by h, and then you take the limit as h goes to 0. If you look back in Calc 1, that was the definition of r prime. That was the definition. What was the definition of f prime of x? What is the definition of f prime of t for a real valued function? It is the limit as h goes to 0, f of t plus h minus f of t over h, right? Isn't that the definition we gave in Calc 1? So, what is r prime of t? R prime of t is that limit, and that's the velocity. Now the question is, what is that limit? Well, let's plug in. What is r of t plus h? What is r of t plus h? That's the position vector at time t plus h. So what is r of t? R of t is x of t, y sub t. So I'm going to plug in r of t to be x of t, y sub t. And I am going to plug in r of t plus h. So r of t plus h would be x of t plus h, y sub t plus h. So plug in the values of r of t plus h and r of t in terms of the component functions, and we get that. And now, how do you take the difference of two vectors? How do you take the difference of two vectors? I have one vector here, another vector here. How do you take the difference? Well, you take the difference component-wise. So you subtract x of t from x of t plus h, and you subtract y sub t from y sub t plus h. That's how you subtract vectors component-wise. Once I have that, then I have to divide by h, right? So dividing by h simply means you divide each component by h. So that means that you are going to divide each component by h. So you're going to get x of t plus h minus x of t divided by h, comma, y sub t plus h minus y sub t divided by h. Now, once you have that, what is the limit of the first ratio? What's the limit of the ratio involving x? What's the limit of the ratio involving x? Well, the limit of the ratio involving x is exactly the definition of the derivative of x at t. X of t plus h minus x of t divided by h. So as h goes to 0, you get x prime of t. Remember once again the definition. Oh, I think I erased it. I have it here. If I take the limit of f of t plus h minus f of t over h, that's the derivative of f at t, right? Same way, what's the derivative? What's the limit? What's the limit of x of t plus h minus x of t over h? That's x prime of t. What is the derivative of y sub t plus h minus y sub t over h? That's y prime of t. So what did we get? We got that the velocity vector, we got a formula for the velocity vector in terms of the derivatives of the position, vector. And we see that the derivative of the position vector is just the component-wise derivatives, right? The position was x sub t, y sub t. You're just taking the derivatives of the components, and you get the velocity vector. Is that making sense? Is everybody okay with that? You will see more on this in Calc 3. Any questions, anybody? Let me know if I have to go up or down for you to write down everything, okay? How is everyone done writing up to this point? Everybody's done writing up to this point? Okay, so what have we got? We got that the velocity vector is x prime of t, y prime of t. That's the velocity at time t. Now, if I take what's the length of a vector? Anyone remembers what's the length of a vector? What's the length of a vector? If I have a vector coming from the with tail at 0, and the tip of the vector, if I have the vector AB, right? If I have the vector AB, then the standard position of the vector is like this, right? If I have a vector like this, what's the length of that vector? What is the length of that vector? Well, the length of the vector would be the distance between the origin and the point AB, right? What is the distance between 0 and AB? I know the distance formula, right? By the distance formula, it is what? B minus 0 squared plus A minus 0 squared, right? And then you take the square root of that, right? Is that the distance formula? You guys remember the distance formula to find the distance between 2 points, right? You subtract the, you take the difference of the x components, square it, take the difference of the y components, square it, add them together, and then take the square root, right? That's the distance formula. So I know that the length of a vector is basically square of the first component plus the square of the second component, and then you take the square root, right? So what is the length of the velocity vector then? What's the length of the velocity vector? The notation we use for the length of a vector is double vertical lines around the vector. So what's the length of the vector, velocity vector? The length of the velocity vector we're going to call the nu of t, and that's the speed. The length of the velocity vector is the speed at time t. And the speed at time t would be then, you take the square of the first component, plus you take the square of the second component, and then you take the square root. And we see that that quantity is exactly the derivative of x with respect to t squared plus the derivative of y with respect to t squared, and then the root of the whole quantity. So that's speed at time. That's speed at time. What is now my question is, what's the distance covered over the time interval from A to B? What distance is covered by the bug over the time interval from A to B, given that I know the speed function, right? Right. In Calc1, remember we said if you are given the speed function of an object, right, and if you want to know the total distance covered by that object, you just integrate the speed function. So if I integrate the speed function from A to B, I get the total distance over the interval from A to B. And so the integral from A to B of the root of the derivative of x with respect to t squared plus the derivative of y with respect to t squared dt. Okay? So if you take the integral of the speed function, you always get the distance. Okay? Integrate the speed function over an interval, time interval, you get the distance covered over that time interval. Okay, so we got a formula for the length of the curve, or the total distance covered by a moving object over the curve, right? Now, how many of you think that this is a proof? That, remember, my problem was come up with the length of the curve, length of the parameterized curve, and we came up with a formula for the length of the curve, right? So this is the length of the curve C, right? We are claiming that's the length of the curve C. Even though I thought of C in terms of the path of the bug, right? I thought of C in terms of the path of the bug. Otherwise, my discussion wouldn't make sense, right? Because I'm talking about velocities and stuff like that. So I'm talking about motion here. But the length of C would be this. This should be the formula. You can think of, I mean, if you imagine, this should really be a formula for any curve. It doesn't have to be the path of a moving object, right? As long as these derivatives are defined, right? If these derivatives are not defined, then I cannot say what I just said. Now, my question to you, is this a proof that that the length of the curve should be this? Did I prove it? How many of you are convinced that this is a proof? You're done. That's the length of the curve. That's the length of the curve. I mean, this is the length of the curve. No matter what curve you have, But have I proved it? Have I justified it, the formula? How many of you are convinced this is it? Just two? No one else is just... Okay, you two are thinking like engineers. The rest of you are not thinking like engineers. Okay. Maybe you guys should change to major in math, right? All right. Let's see how we can prove this. Okay. What's the problem? What's the problem with what we did so far? The problem is, let me ask you this. What is the meaning of the length of the curve? What's the meaning of the length of the curve? If I give you a straight line segment, there is no doubt what is the length, right? A straight line segment, no confusion, what's the length? But if I have a curve, what is even the definition of the length of the curve? What do you mean by the length of the curve? Can anyone tell me that? You see the problem? You don't have a good definition of the length, but yet you're saying the length formula is, you found it, right? Am I making sense? So in order to make your argument precise, what we did was fine. I mean, as a physicist, you would probably do that. Okay? If you're a physicist, you would probably just do that. But in math, we want to have like a precise, logical proof of why that's the case. And if I want to do that, I need to give you a definition of what I mean by the length. Okay? So what would be a good definition of the length of a curve? Well, this is how we're going to think about this. Before you come up with a definition, think about what's a good way of approximating. What would be a good way of approximating the length? By using something we know. What do we know? We know the length of a straight line segment. Everybody understands the length of a straight line segment, and we want to use that and try to come up with an approximation of the length of the curve. So what's the idea? The idea is, okay, let's pick points on the curve. So what I did here, I picked n points on the curve. So I picked P0, that's the point at time A. P1 is a point on the curve which is achieved at time T1. P2 is a point on the curve achieved at time T2, and so on. And there is a Pi minus 1. There is one arbitrary point Pi minus 1. That's achieved at Ti minus 1. Pi is a point achieved at time Ti, and so on, all the way up to Pn. So all I did here is basically I picked certain points. I picked n points on the curve, and then I'm going to look at consecutive points, and I'm going to add them by a line segment. So add consecutive points by a line segment. So I have all these pink line segments, right, between consecutive points that I picked. Now look at the total length of the line segments, right? Each line segment, I know what's the length. Right? I'm going to show you in a second what's the length of each line segment. But if I look at the total line segment, if I look at the total length of the pink line segments, am I getting an approximation for the length of the curve? The answer is yes. Not only that, imagine that I pick more and more points. Imagine that n is 1,000, 1,000,000, 1,000,000,000, more and more. Imagine that, and then these line segments are becoming tinier and tinier, right? And am I getting better and better approximation? If you pick n big, these points are becoming very, very close to each other. If these points are very, very close to each other, your approximation is getting finer and finer, right? So the idea is that, well, we are going to define the length of C in the following way. We're going to say that the length of C is approximately the total length, this sum is over I going from 1 up to n. Basically, I'm looking at the length between Pi minus 1 and Pi, right? And then when I goes from 1 to n, right, when I is 1, you get the length between P0 and P1. When I is 2, you get the length between P1 and P2 and so on. So this summation gives you the total length of the pink line segments. You agree with that? This summation. So if I take the limit as n goes to infinity, whatever quantity that I get, I am going to define that quantity to be the length of the curve. Is that making sense? This is the definition of the length of the curve. The length of the curve is defined by the limit as n goes to infinity of the total length of the pink line segments. Is everybody okay? So now I have a definition of what I mean by length. Okay? The next thing that I want to do then is show that the limit, I want to compute the limit now. I want to show that the limit is equal to whatever formula the physicist arrived at. Okay? Is everybody clear? How we are defining the length? Right? You pick points on the curve. You look at line segments between consecutive points. You take the total length of the line segment. That's an approximation to the length of the curve. And then you just see what happens as you pick more and more points. As you pick more and more points, the total length of the line segments will converge to a number, and whatever that number is, that's the length. Now, what's the problem then? Well, the problem is I have to go from this limit to this formula here. Okay? This is where things would be a little bit harder. Okay? So, first of all, I want to look at what is that limit, what that limit is, right? Now, remember, if you have a definite, we claim the length of the curve is a definite integral. We know definite integrals have to do with what? Riemann sums, right? Riemann sums, and you take the limit of the Riemann sums, you get definite integrals, right? Well, this limit here should remind you of that, right? This limit here should remind you of that. So all I have to do is make this limit, make this sum look like a Riemann sum. If I make this sum look like a Riemann sum, then I'm done. I know what the limit is. Am I making sense? We're going to get there in a second. But first of all, what's the length? What's the length between pi? What's the length of the line segment between pi minus 1 and pi? What is pi? Remember, pi was achieved at the time ti. So what are the coordinates of pi? The coordinates of pi would be x of ti and y sub ti, right? Remember, x of t, y sub t is the x of t and y sub t are the functions for the x and y coordinates, right? So pi would be x of ti, y sub ti. What are the coordinates of pi minus 1? Pi minus 1 is achieved at time ti minus 1. So pi minus 1 will have coordinates x of ti minus 1, y sub ti minus 1. Now, can someone tell me what's the distance between pi and pi minus 1? How do I find the distance between these 2 points? Well, I use the distance formula, right? What's the distance between 2 points? It will be x of ti minus this squared, y sub ti minus y sub ti squared, and then you take the square root, right? Am I right? So, what's the distance between pi and pi minus 1? The distance between pi and pi minus 1 is root of xi minus 1 squared plus yi minus 1 squared. And then, x of ti minus x of ti minus 1 squared, y sub ti minus y sub ti minus 1 squared. I'm just calling them by this, but this is what I get. That's the distance between pi and pi minus 1. And then, here is where it becomes a little bit complicated. This expression that I got for the length of the line segment between pi and pi minus 1, I have to rewrite this. And I have to use the mean value theorem to do that. So we are going to apply the mean value theorem for the functions x of t and y sub t. How many of you remember mean value theorem? Okay, let me remind you very quickly here. What does the mean value? Okay, first of all, remember what x of t is. X of t is the x coordinate, right? If you think about the position vector, if you look at the position vector, what is x of t? X of t is the horizontal component of the position vector. Y sub t is the vertical component of the position vector, right? So if you have the position vector out of t like this, then x of t is the horizontal component, y sub t is the vertical component, right? Now, I am going to apply the mean value theorem to the x of t function on the time interval from ti minus 1 to ti. What does it mean? What does mean value theorem says? Well, if you think about x of ti minus x of ti minus 1 divided by ti minus 1, what is that quantity? Well, this is the change of x divided by the length of the period. What is that? That's the average rate of change of x over the time interval from ti minus 1 to ti. So over the time interval from ti minus 1 to ti, the average rate of change of x is given by the ratio on the left. Average rate of change of x means what? The average horizontal velocity, right? This is the average horizontal velocity, and that's going to be equal to the instantaneous horizontal velocity at some time in that time interval. So the average horizontal velocity is equal to what? The instantaneous horizontal velocity at some time in that interval. Now this is for any x, so it doesn't have to be about motion. So if I have this average rate of x, that's the same as instantaneous rate of x at some time. Same thing happens for y. So I can also say the same thing for y, that the average rate of change of y over the time interval is the same as the instantaneous rate of change of y at some time, at some number in that interval. Okay? So what am I going to do then? Well, I am from here, the change of x, I can say the change of x is equal to x prime of ti star multiplied with ti minus 1. Same thing happens here. The change of y can be written as y prime of si star multiplied by the length of the period ti minus 1. So I'm going to rewrite that. The length of the period ti minus 1, I'm going to write it as delta ti. Delta ti is basically the denominator, ti minus 1. And so I'm going to rewrite the change of x and change of y, and then I'm going to plug them in. Remember, in my distance between pi and pi minus 1, I have the change in x and the change in y, right? I'm going to plug in now those values that I got. And if I plug them in, I am going to get x prime of ti star squared, delta ti squared, y prime of si star squared, delta t squared, okay? So here, when I'm taking the square like this, okay? So then, delta t can be factored out from the square root, and you can rewrite the square root the way I did. So what do I have inside the square root then? All I have inside the square root is the x prime of ti star squared plus y prime of ti star squared. You might say, why I had a si star, right? Why do I have ti star now? Well, I'm assuming that n is so big that the intervals are so tiny that y prime of si star and y prime of ti star are about the same. Very tiny interval. If I have this now, what is the summation? So if I look at the summation and the limit as n goes to infinity, summation of the length of the line segment between pi and pi minus 1, if I look at the summation, that summation is now looking like the summation I going from 1 to n, the root of x prime of ti star squared plus y prime of ti star squared. And if you look at that sum, this sum that I have here, this sum is the Riemann sum of what function? That sum is the Riemann sum of exactly the integrand that I have here. If I look at the integrand function in my integral, the Riemann sum of that function is exactly that sum. So when I take the limit of that Riemann sum, I'm going to get the definite integral. Is that making sense? A little bit more painful to make it more precise, but it could be done. Okay. The main idea is that I have to have a definition of what I mean by the length, and then once I have a definition, then I have to show that the definition, I can work out the definition and come up with a formula for the distance or the length. So finally, all you want to remember now is that if I have a parameterized curve like this, where x of t and y of t are the component functions for the curve, and the curve, the parameter t varies from a to b, then what's the length of the curve? What we are saying is that the length of the curve is given by this integral, right? The length of the curve is given by that integral. Is everybody okay? That's the formula that you need to remember. The length of the curve. It's a very easy formula, right? All you're saying, that you take the derivative of the component functions, you square them, add them, take the square root, right? And then you integrate from a to b. One thing that I forgot to mention here is that you have to make sure that as t varies from a to b, the curve is traced exactly once. Because from a to b, if you trace the curve twice and you compute the length by using the formula, you're going to get twice the length of the curve. Am I making sense? So you have to make sure that the curve is traced exactly once. Otherwise, you'll be getting twice the length. Well, I think it's a good moment to do an example, okay? So I have the curve C, and I want to find the length of the curve C. How would I do it? What is the length of the curve C? Okay, and well, the formula is pretty easy. I have t varies from where to where? T varies from 0 to 3. Now I have to make sure that as t varies from 0 to 3, the curve will be traced exactly once. How do I know that's the case? Well, if you look at it, as t varies from 0 to 3, what is happening to y? Y is a straight line as a function of t. Y is a straight line as a function of t. So as t varies from 0 to 3, y is actually decreasing, right? So this curve was not traced more than once over the time interval. Why? Because if the curve traces more than once, then you're going to get the same point twice, right? You're going to get the same point at two different values of t. However, that's not possible in this case because you cannot get the same value of y twice, right? You cannot get the same value of y twice at two different values of t because y is a one-to-one function. It's a straight line as a function of t. So I know, usually you don't have to worry about it, but I'm just saying that you can verify that the curve is not traced more than once. So you know that it is traced exactly once, so you now integrate from 0 to 3. So t goes from 0 to 3, I know that. And then What do I integrate? Well, I take the square root of what? I take the derivative of the component function. So what's the derivative of x? Derivative of x is e to the t minus e to the minus t, right? And then I take the square of that. And what's the derivative of y? Negative 2 square of that, and then dt. Am I right? And then, well, once I have the integral set up, it's just a matter of computing it, okay? It's a matter of computing that integral. And let me not compute this integral today. Let me do it maybe tomorrow, because I need to finish up some other business here. Everybody's clear? It's just a matter of computing this integral. I'm going to show you how to compute this integral tomorrow. But what I want to do is think about the following problem. Here, I don't have a parameterized curve. What I have is the graph of a function. I have a graph of a real valued function f of x. And I want to know what's the length of that graph is. So here, the problem is different, okay? So what we are saying here then is the following. I have, let me, so here what we are saying is that we have the graph of a function f of x, let's say between a and b. So this is the graph of f of x between a and b. This is not a parameterized curve. I want to know what's the length of this curve, okay? What is the length of this graph? Now, this is not a parameterized curve, so I cannot use the formula directly, right? So what should I do here? Well, remember we talked about if I had the graph of a real valued function, I can parameterize it. So what would be a parameterization of this of this graph? What can I pick for x? And what can I pick for y? I want to parameterize this c. So let's call this graph c. What would be a parameterization of that c? Well, can I pick x to be just t? And then if I pick x to be t, then what can I pick for y? Well, y has to be what? F of t. And then what would be the interval for t? Well, t is the same as x, and we know that x is going from a to b, right? Here is the x-axis, y-axis. We know that x is going from a to b. So I know that t has to go from a to b then. So this is the parameterization of this graph, right? So now I can apply my formula for this length. What would be the length? The length would be the integral from a to b, the root of, what is x prime of t? What is x prime of t? 1 squared. What is y prime of t? Y prime of t is the same as f prime of t, right? So I take the derivative squared and then dt, right? Derivative of x with respect to t squared plus the derivative of y with respect to t squared, and then you take the sum and then you take the root, right? This is it. So then note that this is the same as what? This is the same as integral from a to b, 1 plus. Notice that I can just write f prime of x squared dx here. It doesn't make any difference, right? Between the integral from a to b in terms of t and in terms of x, there is no difference, right? Instead of calling the variable x a variable t, I'm calling it x, right? Again. So this is the length formula. This is the length formula if you have the graph of a real valued function. Okay? So, for example, let's look at this function here. If I have this function, what would be the length of the graph? I don't even have to draw the graph of that function, okay? I have a function there, and x is going from 1 to 3. X is going from 1 to 3. So what would be the length of that? What would be the length of the graph of this function? Well, by my formula, now I'm going back to my problem. By my formula, remember x is going from what? 1 to 3. So x is going from 1 to 3. and I take the square root, it will be 1 plus the derivative of the function squared. What's the derivative of the function? What's the derivative of this function? Yeah, f prime of x is what in our given example? Half of x squared minus half x to the negative 2, right? You agree? You agree? I'm going to get half x squared, and then what's the derivative of half x to the negative 1? The derivative of half x to the negative 1 would be negative half x to the negative 2. So what am I getting? I'm getting half x squared minus half x to the negative 2, and I'm going to get the square of that and dx. So that would be the length. That would be the length of the graph of the function f from 1 to 3, right? That integral is going to give you the length. Now, again, you have to compute that integral. Again, I'm not going to show you how to compute that integral yet today, but I want to give you one more thing here, which is, suppose that now I have a curve which looks like the following, where I have, let's say I have a curve which looks like this. Okay, here is D, here is C. Now this curve doesn't represent y as a function of x. However, it does represent x as a function, right? X as a function of y. So let's say x is g of y. So if I have x as a function of y and the graph of that function, how do you find the length? Well, the length of this, let me call that curve C. Sorry to use both C and C there, but you'll deal with it. The length of C would be lowercase c to the lowercase d, and then it will be the same formula, 1 plus, instead of f prime of x, it will be g prime of y. G prime of y squared and dy. So that's the formula for a curve like this. And finally, let me just give you a very quick example on this. Let's say I have the following function. If you look at the graph of this, this is the graph of x equals to y squared. So this is my g of y. This is my g of y. Let's say we are looking at between -1 and positive 1. So we are looking at a finite part of this parabola, right? So what's the length of the, let's say the red part of the parabola? So that's what I want to know. And the length of the red part here, y is going from -1 to positive 1. I take the square root and I get 1 plus, and I take the derivative of x with respect to y, and the derivative of x with respect to y is what? 2y, right? That's the derivative of x. So here, when I look at the length of c here, right, this length of c you can rewrite as the integral from c to d, root of 1 plus dx dy, right? Dx dy. Dx dy. So you take the derivative of x with respect to y. In the previous formula that when I had, in this case you can write the length formula as integral from a to b, the root of 1 plus f prime of x is dy dx, okay? Dy dx. Right? F prime of x is dy dx, and g prime of y is dx dy. That's the difference. But otherwise, same formulas for both situations. Tomorrow I will show you how to compute these integrals. So